Thank you for the generous introduction. It's really good to be here today. I think the last time I was in this building was in 2014. It was for Y Combinator Demo Day, and I had 2.5 minutes to pitch a full-stack quantum computing company before really any of this existed. So it's good to be back, and thank you for the luxurious 30 minutes. This is going to be great. So I'm going to talk to you today about quantum cloud services and Rigetti computing, and tell you a little bit about how we see the world going forward in terms of what's required to get to quantum advantage. So when I started the company in 2013, one of the very first things I did was write down a mission statement. And that mission is to build the world's most powerful computers. How we think about doing that at Rigetti is by building these quantum processor units like this. This is an example device. It's a 20-qubit chip based on our kind of first-generation processor technology. And then integrating those quantum processor units, or tightly integrating those with advanced classical computing infrastructure like compute, networking, and everything that's needed to run it as a real full computing system. And that's ultimately led us now to building what we call Rigetti Quantum Cloud Services. And this is a hybrid quantum classical platform for computing over the cloud. So we make those chips in a facility across the bay in Fremont here that we call Fab 1. So Fab 1 is a dedicated, purpose-built facility for the design and manufacturing of quantum integrated circuits. And I'm going to tell you a little later at the very end of the talk some of the results we've been able to achieve this year based on operating this fab in a kind of rapid iteration mode, which is really unlike how most semiconductor-style fabs operate. And we've been getting really exciting results based on that. Now, a typical chip looks like this. Again, this is our first-generation technology. This is a die that has 10, 12 different 8-qubit chips, and what would happen next is this die would be diced up into chips, and those chips would be sent to our quantum engineering lab up in Berkeley, where they'd be integrated into a cryogenic system, and then a computing system, and tested, and eventually potentially deployed over our cloud web API, or now our quantum cloud services capability. So this is what that quantum engineering lab looks like, and this shot is now about 2 years old or 18 months old. You can see a bunch of the fridges. This is a gritty shot. It's a little less produced than some of the other stuff you've seen. This is a regular workday at Rigetti Computing in the engineering lab, and I think there's 8 different prototype quantum computers here at different stages of production and integration and evolution. And I want to call out what's really happening now. So basically, like the cells in the human body are replaced kind of every 12 months or so, we're basically rebuilding the infrastructure in this lab and evolving it from a quantum engineering lab into what I think of as one of the very first quantum data centers. And we're not there yet. It's not really at full kind of commercial or enterprise production capability, but that's how we think of evolving this technology over time, slowly improving the capability to deploy and serve these machines over the cloud to end users. So for the so between 2016 and around 2018, what we were really focused on was building these first-generation Rigetti quantum processors. And this is a typical kind of aluminum on silicon process. This is a 4x5 array of superconducting qubits. It's based on a lattice of alternating fixed and tunable transmons. And Alan, I disagree with you. You don't need every qubit to be tunable. Every second one is just fine. And so, typical coherence times in these chips was on the order of 10 or 20 microseconds by the time we got it really working. In this particular device is a 20-qubit chip, but we called it 19Q because one of the tunable qubits wasn't actually tunable in practice, and so we didn't employ it in any of the demos that we did with it. So then what we did is we built these chips. We learned how to make them work reasonably well, and then we deployed them over what we called a forest web API. And we're one of the very first companies to do this. In that web API, you would have a Forest server that we hosted in that instance on Amazon Web Services. And the Forest server would send jobs to the QPU or to a classical computing capability, also in AWS, and would run hybrid algorithms on that capability. And ultimately, the Forest server also called a compiler every time you need to recompile the circuit. That Forest server, or that web API model, included our Forest software development kit, which is a Python-based software development kit. It was the first one to have that capability. And ultimately, this was all based on and was a manifestation and instantiation of hybrid computing for the very first time. And I'm really excited to see much of the hybrid effort being taken up by major players now. This really goes back to this kind of seminal paper from Robert Smith, who's one of our architects, back in 2016, when we defined for the first time an instruction set for hybrid quantum classical computing, an instruction set that put the two kind of quantum information and classical information on the same footing, so you could really think about how to build a hybrid algorithm, and then execute it at runtime. So I want to quickly talk through one of the funnest things I think that we've done with these machines over the years, and that's this solving a clustering problem with Eddie Farhi's quantum approximate optimization algorithm. So how this really works is you have a set of points, okay, and the set of points. What you want to do, they're unlabeled, and what you want to do is assign labels to those points based upon some sort of similarity metric. In this case, we used a Euclidean distance. And what we did was we took the set of points, you map it onto a planar graph, then you treat it as a max cut problem for which you can use a quantum approximate optimization algorithm to solve through an optimization routine. It's a classic, it's a traditional, like a really great example of a hybrid algorithm and what you can do with it. So this is a canonical, unsupervised learning problem, and this is a toy model. This is not ready for commercial production. This is not ready for real enterprise workloads. It's not close to being so. But it, for the first time, put all the pieces together, from designing and building a chip, to manufacturing that chip, to operating as a real gate model programmable quantum computer, and then going all the way up to a real application that you want to solve. And this clustering problem is actually the algorithm that is run to recommend you movies or TV series you might want to watch on the weekend on Netflix or Amazon Fire TV, or the friends you might want to connect with on Facebook. This kind of clustering problem is a really, really important one in industry. And so for the first time, we're able to put all those pieces together. What we learned by doing that was really, really critical. In these hybrid algorithms, what you do is you put a quantum processor unit and classical computing on the same footing, and you operate them within a single optimization loop. So how it would look like, this is how it might look like for the QAOA algorithm, in which case you're optimizing the rotation angles applied to single qubits within the computation. And so you'd select an initial guess at what those angles are. You create a program with those selected parameters, and then you send that to the quantum processor where it's compiled into a program for execution. You execute those instructions, you measure the output, you record the data, and then you send the data back to classical processing, and then you use that data to evaluate some real valued objective function. You compare the value of the output of that objective function to some halting criteria, and then most likely you continue that loop for 1,000, 10,000, potentially 100,000 times. That's how optimization algorithms work, and this is an illustration of generally how these hybrid algorithms work. Now, I don't know where the first applications are going to lay. I don't know which companies are going to be the first to achieve quantum advantage. A lot of that, frankly, depends on you and how you decide to engage within the industry. Or with the players that are building these machines today. But what I do know is that hybrid algorithms on integrated quantum classical computing systems are going to be the first to show quantum advantage and to unlock real business value. And if you view your organization as being a serious player in pursuing the power of quantum computing and getting there first to create value within your business, then you need to be working on a platform that is hybrid first and that has this capability. So based upon what we learned in this first generation, we've gone now and we've moved beyond the web API model. And earlier this year, about 3 months ago, we announced Rigetti Quantum Cloud Services. This is the first and the only true kind of quantum-first cloud platform that's out there today. And it combines a bunch of innovations that accelerate the hybrid compute performance of the overall system. So the first one I want to highlight is what we call co-location. So taking the classical computing and situating it right next to the rack that controls the quantum computer saves you about a factor of 4 in the overall, or it can save you up to a factor of 100, in fact, in the latency. And it shortens the latency so much that it becomes an irrelevant factor in the overall compute time. So what we've done is put all these things together: the classical compute, the quantum processors, the compiler server, and hosted that all within our emerging kind of quantum data center in Berkeley. So the co-location gets you a really significant speed up. And then in these optimization algorithms, one thing, so Alan called out the challenges that have been exposed or that have been talked about recently in the past year by the Google team about barren plateaus and optimization within of parameters within QAOA or VQE. And in fact, there are gradient-free methods that can be used to solve these optimization problems, and that's what we did to solve this clustering problem with QAOA. So we had to work really, really hard on the classical optimization, and we ended up using a Bayesian approach that is a gradient-free approach. And what that means is that in a gradient-free approach, you don't actually care about the order in which you acquire the data that you're optimizing over. You can get it in one shot or multiple shots, and then process all of that using the Bayesian optimizer. And so what that leads to is you can generate significant lift for your algorithm performance by doing what we call parameterized program compilation. So you can send a single job to the quantum processor that gets back 100 or 1,000 samples of the different angles that you're optimizing over in one shot. And what that does is, in addition to the co-location reducing the round-trip latency, this reduces the total number of calls you need to make and total number of round trips. Now, the other thing is, as the coherence times improve, and I'm going to show you at the end of the talk some of the recent progress on that, as coherence times improve, the coherence time starts to work against you because with every call of the hybrid algorithm, you need to wait for the qubits to relax back to the ground state to initialize to start the program again. And so what we've done in our new QPUs is to create this option that allows you to turn on active reset. And so you don't need to wait for a full T1 or multiple T1s to run the next shot of the algorithm. And in the shallow depth circuit, this can give you a lift of up to a factor of 20 or so in performance, depending on the coherence times and the depth of the circuit you're running. So when you put all those things together, you get a really significant performance lift. And then the other thing I want to talk about is this is a quantum machine image. So if you look at how the public cloud services are architected today, on AWS they have, and they coined the term really, the machine image, the Amazon instance, pardon me. Look at DigitalOcean. DigitalOcean calls it a droplet. So it's basically a pre-configured machine image that you get to start developing and start running programs and eventually to build production workloads into those machine images. And we built Rigetti Quantum Cloud Services inspired by that same direction, okay? So you get what's called a quantum machine image, and today the QMI comes pre-configured with our Forest software development kit. And you can get started. One of our people on the marketing team was able to get started within 10 minutes, so I'm sure all of you will be able to do the same. So when you put this all together, what you get is an integrated quantum classical cloud platform that's about 30 times faster than web API access models. So to benchmark that a little bit, if you look at what I'm about to show you on the next slide is a short video that shows this benchmark of the performance increase you can get on Rigetti QCS relative to web API models. What I'm going to show you is a 2-qubit quantum approximate optimization circuit being run in with three different settings on our platform. And you're going to compare that against it would take typically about 100 or maybe 200 seconds to run this on, for example, IBM Quantum Experience or on the Rigetti Forest 1.x generation of web API capability. And so what you'll see is that co-location cuts that down by about a factor of 5. Then you get successive factors of 3 by turning on these performance these flags that are parametric programming, and then active reset as well. So we can go to the video. No one likes waiting. Okay, so let's go to the next slide. So to the next one, please. So can go back. So what you see is it's about 35 times faster than what you got with the earlier web API model. And 35 times is a really significant amount for when you're working in a world where these algorithms are being used for iterative development. Quantum computing today and hybrid algorithms are a sandbox, and our cloud services platform is a sandbox in which we can now develop for the very first time interesting hybrid algorithms and test those and learn empirically based upon their performance. Okay, so this is a quick screenshot of our quantum cloud services platform and what it looks like. So you have a quantum machine image with a dedicated IP address. You can connect to your QMI, and you can get up and running, building software and building quantum applications within that QMI today. On the right, what I want to highlight next is this. Our second generation Aspen quantum processor units are now available live on the platform. So this is a 16-qubit chip that you can run on today. And the Aspen QPUs are, as I said, this is really our second generation QPUs. And what we've done is we built this first generation technology for 2 or 3 years. That was a simple fab manufacturing process based on simple aluminum on silicon. And what we've gone now is step back and say, what are all the pieces that we need to put together to really get to the level of performance and scale that's required to achieve quantum advantage? And what we've decided, and what we've learned from doing that is that you're going to need to probably get, for quantum advantage, you're going to need to get above 100 qubits, and you're going to need the error rates to be below 99%, potentially below 99.5%. Okay, it's similar to what are the error correcting thresholds that are known. And so we built this Aspen fabric, qubit fabric, that is based upon alternating fixed and tunable transmon lattices, fixed and tunable transmon qubits, and those qubits are arranged into what's called a 488 lattice. This is alternating octagons and squares. And what this is a scalable qubit fabric, and the reason we call this Aspen is because these Aspen groves, many of you will know this, so these Aspen groves actually spread and grow through the root system. And every Aspen tree in a common grove, and the groves can be hundreds or thousands of hectares in size, all the trees in a single grove are genetic clones of one another. And so within this qubit fabric, what we're doing is designing a specific Hamiltonian and a specific fab and lithography mask, optimizing that at the 16-qubit scale. And then you copy and paste that fabric to produce ever larger chips. You don't need to redesign the Hamiltonian. You don't need to redesign the circuit. You just scale it in a straightforward manner from 16 to 32 to 64 to 128. And so we can optimize the 128-qubit Hamiltonian at this smaller, cheaper scale at 16Q. So the thing that I'm most excited about with respect to the Aspen, with respect to the Aspen chips is, for the first time, this is the chip platform that is going to allow us to put together all of the different ingredients that are required for both performance and scale. The first thing you need, of course, are high coherence qubits and high fidelity logic gates. And I'm going to talk a little bit more in the next few slides about recent progress on that. Then you need to create a packaging environment, an electromagnetic environment for the chips with a superconducting caps that are bump bonded onto the qubit IC. And then we're introducing into the qubit IC superconducting vias that allow you to separate and isolate qubits from one another and achieve better electromagnetic control. And that's also essential as you scale up the number of qubits. You need to use a bigger chip. And those larger chips develop resonance modes if you don't use superconducting vias. And so this is an essential technology to getting towards advantage. So one of the things I want to highlight, and what to look forward to in 2019 and the next year or two on quantum cloud services, and this also, this highlights what we've been able to achieve using Fab 1 in rapid iteration mode. So because we have this facility and because we design and build all of our chips in-house with our dedicated manufacturing team, we're able to do very rapid design iteration. We're able to do very, very carefully controlled process variation. And to do that with statistically significant sample sizes, and to do very careful A/B testing of different process variations. And so one of the things that we've been able to do over the past, this was about a 3-month project that took place in the second quarter of this year. Ultimately, we started with our 20Q first generation processor as a baseline capability, and we started by optimizing the quality factor of our superconducting resonators. And what we saw by going through this deterministic march of just testing, building testing, and then feeding back on that, we're able to go from around 200,000 quality factor to above 1 million reliably in a statistically significant number of resonators in each chip. Over the matter of about 3 months. And this is what you can do when you have your own fab capability and you're operating in this mode. And so then the next thing we did was went and, this was based on superconducting resonators, went and built qubits out of that. And so now we're able to achieve coherence times that are effectively on par with what the leaders in the field are getting, in many cases above 100 microseconds. Now, the next thing I want to talk about is 2-qubit gate fidelities. As I highlighted, it's going to be necessary to achieve at least 99% fidelity in your 2-qubit gates to get to quantum advantage or to get to supremacy. And we now feel like we have a very clear path to getting towards that. So we've been able to demonstrate for the very first time on a chip that is on an 8-qubit version of an Aspen chip, the very smallest segment that we've produced, 2-qubit gates with reliably 99% fidelity or higher. And so what we found in this particular gate, we studied it extensively to really understand what was going on, is there is statistical fluctuations of the coherence of the energy relaxation time, so T1. And that's very common in superconducting qubits. It happens in almost all the devices we've seen, usually by a factor of 2 or 2.5. So in this case, a factor of 2.5 fluctuation in T1 was leading to about a similar factor of fluctuation in the effective fidelity of the 2-qubit gate. And what this tells you is that you understand the Hamiltonian that you're building, you understand the quantum system that you're engineering completely. And in order to increase the fidelity of the 2-qubit gate, you need to increase the coherence time. So you've understood it, your process works. And the way that, the reason this really worked is because we're doing these parametric gates we've developed at Rigetti Computing. And these parametric gates, ultimately, we found that there's what's called a sweet spot, or a dynamical sweet spot, when you drive the 2-qubit gate at a particular frequency and amplitude, that you can drive it back to a place where you're insensitive to dephasing. And that allows us to achieve these very high fidelity 2-qubit gates. So in this particular instance, about 11% of the data with the T1 fluctuations was better than 99% fidelity, and 100% of the data was above 98% fidelity. So when you combine this with the coherence times improvements, this was in a device that had coherence times between 12 and 30 microseconds. When you combine this with a 3x performance improvement in coherence times I just showed you, we expect that we're going to be able to push those fidelities below 99 or above 99.5%. And that's a very exciting thing to look forward to on quantum cloud services. So kind of putting all the pieces together, when you look at the scaling of the Aspen chips from 16 up to 128 qubits with these performance improvements that we've been able to achieve, we thought it was time to start to align the effort of a broader community than Rigetti Computing can bring to bear towards the achievement and demonstration of quantum advantage. And quantum advantage is a term that we prefer. We think that it really calls out what is important about this pursuit of quantum computing, and it's delivering some sort of advantage to end uses, to business, right? And so quantum advantage is the ability to solve a problem better, faster, or cheaper than you can do without quantum. It's very simple. It bakes in all the potential for reducing electricity costs, for reducing data center costs, for accelerating the runtime of algorithms in general, and also just making it easier to represent problems. And so the Quantum Advantage Prize, we're offering $1 million for the first team that can conclusively demonstrate quantum advantage on quantum cloud services. And to adjudicate that prize, we pulled together a really amazing team that we call the Quantum Advantage Prize Board that is going to act effectively like a Supreme Court to adjudicate whether quantum advantage has truly been achieved in the particular experiment or a particular demonstration. Now, what we're doing, how we think of the world is that we're building the computing platform. So we build the chips, we integrate that, and we deploy that over quantum cloud services. We're building the integrated quantum classical capability. But we need help from an ecosystem of applications researchers and developers and people who are building software on top of quantum cloud services. And then we also need this other piece from industry. We need impactful problems to solve. And no party, no cohort can kind of do this all alone, but through this collaboration, and what the prize does is give us something to align all of our efforts towards that. And so we work with companies to help them define the right kind of problems. We work with partners in our ecosystem to build to do algorithms work towards solving those problems and running them on our quantum cloud services platform. So we're represented here also by Nima Alidoost and Lauren Rugani, so I invite you to come find one of us. I'd love to talk more, and thank you very much for your time.
So, Chad, you mentioned that co-location gives you a lot now.
Sorry, who's talking?
I'm talking.
Oh, hi. Yeah.
And when you look forward to when you, I presume, start doing error correction, do you expect co-location in the doer from the rack to also be required?
So the co-location is, did you say doer?
From into the cryostat.
Yeah, I don't, look, there might be a need. Are you asking if we've already pushed the control system into the cryostat?
Do you expect to need to move the control system into closer location?
Yeah, I see. I think it's possible. I don't think that that is at all required to get to quantum advantage. Okay. When we talk about running large-scale quantum error correction, that's going to happen long after we get to quantum advantage. And going from 100 to 10,000 qubits, yeah, it's going to be natural at that point in time when you have that level of engineering mastery of this technology to start to push much of the control electronics into the fridge. But I don't think that's a really significant requirement to get to advantage at all today. So I think that's inevitably going to happen, but it's not critical right now. Thank you for the question.
Thank you very much. Thanks. Great talk. Demo. Thanks.